Hey, John here. Let's look at how to program the SIO, the serial I/O controller, on the Z80 Retro board. So I'm in the GitHub project page for the Z80 Retro board in this tests subdirectory here, and I'm going to go over this right here, the Hello SIO1 example program. So here's where I have cloned my repo, and you can see about this in the part 1 on the system board testing software video. It'll be in the link in the playlist that I'll link to below in the video on YouTube here. So here's the programs here, and we're looking at SIO1.asm. So, the usual stuff here. Here's a little program to test SIO in pulled mode. I'll do another video on interrupt control mode. It's more complicated. Let's just get this thing to go, all right? So, I've got a label in here that I've equated to 0 or false. And the idea is this program has a lot of stuff stubbed in. So right now, this has me commenting out a hex dump routine that I'll talk about later. All right, so if you set it to 1, it'll print and do more fancy stuff, but in 0, it will disable it and keep things as simple as possible. All right. First thing we do is we include the equates for the I/O ports. I talked about this last time as well. We define where the stack is going to be, which is the end of the memory. We do the usual thing, copy the contents of the flash into the SRAM, and then turn off the flash, fall down here, initialize the stack pointer. Because this is set to false, none of this matters right now. And we call some initialization routines to set up the SIO. Then we fall down here. This is commented out, so it does nothing. We call a subroutine called hello A. These are all then commented out, and I go into an endless loop and halt the CPU. So what is this thing doing, right? All it's doing is initializing the SIO. It's going to call this one subroutine and then stop. What does the subroutine do? One character at a time. It prints out a carriage return, a line feed, hello, and another carriage return, a line feed. This right here prints out the second of 2 L's, right? So if we look at the source code to this little routine here, we'll see that what it does is it takes the character that's in the B register and writes it out the serial port. This then returns back up to where it was called up here, and it falls through, and there's the halt loop. These other subroutines are not used yet. These are all stuff that's commented out. You'll see an include right here for the SIO driver routines. Okay, so inside there is where the SIO init and these other functions are, like the transmit character routine and these guys up here, right? The init calls that we saw up here. All right, so let's go ahead and look at that, which is right there. So what do we got here? We got a couple of routines. We don't worry about these right now. They're not even called in this routine. All we did is call the SIO A init and the SIO B init routines. Okay. And then later on, what did I do? I called the transmit character. In fact, I called SIO A transmit character. In this example, we're not yet using the SIO B, right? The SIO chip has 2 channels. Right now, we're only worried about channel A. Okay, so let's walk through these codes and see what's going on. First thing we do is we call init on SIO-A. Let's look at a little bit about how these routines work. The main init logic is right here. And the way this works is you load register C with which one of the ports, either A or B, that you want to initialize. But the rest of this code down here is the same for each port. So what happens is if I call SIO-A init, I end up loading the A control port address into the C register, and I fall down and return. If I call SIO-B init, I load the address for the B port of the SIO into the register C. I jump over this down in here and run this and fall through and return to the caller. All right. So the entire init logic is right here then. Okay. So let's look a little bit more closely at what happens in there. So ultimately it boils down to this otter function right here, this instruction. And what this instruction does on a Z80 is it will continuously output to the port in the C register, which is what we initialized before we fell down here, bytes that it reads out of memory, starting at the address in the HL register, and it will write as many bytes as there is a number, a counter in the B register. Now, if you don't know how this thing works, go over to the Z80 user manual, which is right here. This is the page inside that manual. This is on, page number 325. It's this manual here. We've seen this before. Just do a Google search on UM0080. That is the code number for this document. You can find it anywhere on the internet. And if you scroll down in here, it'll go over in the table of contents. There's a big list of all the instructions, and the outer instruction, I should say, is right here. Click on that, and that's what we're looking at, okay? So this gives you a rundown of what this thing does. It says the instruction encoding is EDB3. It's a 2-byte instruction, and it performs this. This is kind of expressed in what we call RTL format. This is not a super duper complete and detailed description of the instruction, but this means that whenever you see something in parentheses in a Z80, it's an indirection, okay? Whenever you see C in parentheses on a Z80 document like this, it's referring to a port number that's in the C register. The parentheses say, we're not talking about the C register, we're talking about something whose address is stored in the C register. And in this notation, it's always referring to an I/O port, especially in an out command like this, okay? You see it over here with the HL register, and what we're looking at is the address in the HL register is used to find a byte out of the memory at the address that is in the HL register. That's what the parentheses mean. It's like putting a star in front of a variable in a C program. So putting it in parentheses means take the pointer value that's in this register and go into memory and get it, okay? So what does it do? It copies 1 byte from the address in memory in the HL out to a port whose address is in the C register. Then we say B, the left arrow means put into the thing on the left. It's like an equals in like a C program or something. B equals B minus 1. So we're counting. That's the counter. Count it down. HL equals HL plus 1. So we're adding 1 to the pointer, and we're decrementing the count. And if you read the narrative down here, it says what this does is it repeatedly does this sequence of steps until B equals 0. If B equals 0 before this starts, it will loop through here 256 times, by the way. All right, it'll all be described down here in this narrative. Okay, and it gives you some examples and says if this is stored here and this is in this register and it does this, that, and the other thing. Okay, read this to your heart's content if that description is not enough detail. Otherwise, read this comment right here. It says go writing B number of bytes from HL into the port that is in the C register here, okay? So what does that then mean? We get these labels over here. What are they referring to? Is right down here. So we load HL with the address that's represented by this symbol right here, which is the address in memory of the first byte that we define down here. DB means defined byte, and the value over here is the value of the byte. It ends in a B, therefore it's binary, so this is 00011000 in binary, and so on, okay? This symbol over here is the value that we put in the B register. And this is not a label of a memory address. This is a value that's assigned by an equate statement. So this thing is setting this symbol here equal to $ minus this label up here. Dollar anywhere in this in Z80 assembler means the current address if I were to put an instruction here or if I were to put a regular label here. That would be the value. So in other words, $ minus SIO init WR equals the number of bytes in this table. Using this means if I add or delete stuff into this list, it grows or shrinks or whatever, this label will always represent the number of bytes that are in between this label here and the equate over here. All right? Why? Because you're going to forget to update this stupid thing every time you add or delete something on this table, and then you got to debug that, which is a nightmare. So this is the technique I always use so that let the assembler figure out the right number of bytes here, okay? So the only thing left now is where did these magical and mysterious values come from that I have to write into the SIO? Okay, so quick recap on what these are, by the way, since I haven't really mentioned this since the last video. These are the I/O port numbers for the port A control on the SIO and the port B control on the SIO. These come from the IO.asm file that's included in the main routine, so they're defined right here, right? These are the data and control ports for each of port A and B on the SIO. Their actual values are determined by the schematic of the retro board and how I decoded the address lines to enable the various chips. Okay, so let's go back in here now and figure out what these magical values are that are written one at a time repeatedly written into the same port over and over again, right? So what this is going to do is it'll write that byte into the output port for the port A control line. Then it'll write this byte into the very same I/O port, okay? And the next one, and the next one, and so on, all right? The Z80 was specifically designed to work this way, the SIO, rather, I should say, was to take advantage of this outer instruction here. Now, the other of this companion book that we were just looking at, UM0081, okay, so we were just looking at 0080 for all the instruction details. Well, the 0081 is the peripheral user manual, okay? And there's a chapter in here for each one of the peripherals, like CTC and the SIO and all this other fun stuff. Now, there's an interesting note in here that you want to read. Now, first of all, let's look at the table of contents. Here's the SIO section. It starts on page 207. They got all this stuff going on, blah, blah, blah. What it does if you want to use the serial I/O in synchronous mode and HDLC. What if you want to use SDLC? What if you want to use this? What if you want to use that? And so on. Well, we're only going to use asynchronous mode, so the vast majority of this document we're not even going to read. We're going to read pages 230 to 235 and ignore basically everything else. So let's go down to async operation. And the number one most important thing that we need to know out of this whole manual is that the parameters that are loaded to configure, they're saying, the SIO, need to be loaded in the appropriate write registers by the system program, and that's what we're writing. And then it notes that WR4 parameters must be issued before 1, 3, and 5. Okay? If you don't read this, you're going to get yourself into trouble. So we need to make sure that this whole manual, the only thing I'm taking out of here is initialize write register number 4 first. Okay? Now, the reason I'm going to throw this manual away and go to another manual in a minute is because when they redesigned this manual, they hired somebody that decided to write an enormously huge number of diagrams and strew them over many pages. All the details are in here. Feel free to read all you want about it, or go over to the other manual, which is this one, where they put all the diagrams on one page so we can see what is going on without killing 87 trees, should we decide to print this out. So what manual am I looking at now? I'm looking at the Family Product Specifications Handbook. This is essentially the data sheets for the peripherals and stuff like that. All right, so this is the 1984 version, back when they hired an artistic staff that would draw pictures that were more, let's just say, useful for an engineer. Modern manuals are just horrible. I don't understand why. If you scroll down in here, you'll see all kinds of stuff about the CPU, the DMA controller, the counter timer controller, and so on. This manual here is the one that I use to learn how to program this thing. And honestly, it just makes more sense than the other one. Now, this is going to be much more terse and probably not mention the magical mystery of doing write register 4 first. So if you're totally new to this thing, you might want to read them both. Ultimately, I'm sure I did. So page 71 is where we're heading in this document. which is this page right here, where they talk about how to use the SIO in a more terse kind of set of language. They give you the pinouts. Again, this is more data sheet-ish rather than user guide. So this is going to tell you about the pins, and I think we saw this before when we were talking about the design of the retro board itself. Talks a little bit about how to set up the asynchronous mode. The entire discussion here is 2 paragraphs, maybe 3, okay? And that's it. And they go into synchronous modes. Well, the other manual has like 20 pages for this, okay? So there's pros and cons to both of these. You'll notice that the asynchronous mode starts here. What do we got? 1, 2 paragraphs, 3, 4, 5 paragraphs, okay? Then synchronous modes is going to have a couple of pages. Synchronous is more complicated. Got a couple of diagrams. Data arrives like this in asynchronous mode. And depending on whether you're using monosync, bisync, external sync, SDLC, or HDLC, it works differently. Thank God we're only going to look at this top one. Super simple. Ignore all the rest. Okay? Now let's look at one thing up here before we go on to too much detail. We are using this to do an asynchronous transfer of data using what's called a UART style protocol. And when you do that, you need to tell it the bit rate that you want to move the bits around. And the key here is you need to have a free running clock. And they mentioned that the CTC or any other clock source could be useful for that purpose. All right. And that's one of the things I did in the retro board design is I put a CTC on there and I wired it up so we could, if we wanted to, use the CTC to generate the frequency for the data transfers. And if you want to change the bit rates, that's what we're going to use. We're going to reprogram the CTC at run at different speeds. But I'm not going to talk about that right now. What we're going to do is we're going to use the clock at the crystal oscillator that's running at 1.84 3200 hertz, right? 1.84 some odd megahertz, okay? And the reason I chose 1.84 blah, blah, blah megahertz is because if you divide it by 16, you get the exact frequency you need for 115,200 baud, or bits per second, we should say, which is a very fast but standard bit rate. And you can also divide it by 32, which would give you 57,600 baud, another standard bit rate. Or you could divide it by 64 if you want, and you'd get 28,800, which is a common modem bit rate, but not so much a common bit rate for like serial, cables, RS-232 type stuff. But yeah, it's there. Okay, great. What about this one over here? I've seen postings on the internet, and I've seen people using the SIO, and they get data errors because they don't know what they're doing, because they never really understood how UARTs work in the first place. And if you want to use a divide by 1, just don't. Why does it let you do this? It's probably because this chip has many other modes. It can run in synchronous mode, it can run in asynchronous mode, and so on. And if you say, take the clock that arrives in the serial controller, and you basically divide it by 1, using it as is, the UART logic just won't work. It'll sort of work, but not always, and some characters will be broken, and you see all kinds of posts about that on the internet, and I'm like, you need to read about UARTs before you screw this thing up. So the short of it is, don't use this divide by 1, and we'll see where that comes up in a minute. If you don't understand anything I just said, at least go over to the Wikipedia page and read about the UART, okay? And down here, it does talk a little bit about it. This paragraph, what is it here? After the required time, blah, 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 blah. It talks a little bit about how the UART figures out data is arriving. And it is the manner in which it does that requires the clock to run faster than the bit rate. And almost universally, it's 16 to 1 faster, okay? If this isn't enough, and this is kind of terse, I agree, I probably should go in there and submit a patch for this to add some more detail. You can read what I read when I learned how to do this 40 years ago, when I could go, you used to be able to walk into a Radio Shack and buy these things and would have them hanging there, unless they, of course, were out of stock. Anybody of a certain age knows that You used to walk into a Radio Shack, and there's the thing you want with a nice card hanging there that says 276-1234. Sorry, temporarily out of stock. So classic. Used to ride my bike across town, and only to find out they're out of stock. But anyway, normally they would have these when they were in stock, and this is the exact number. You can still buy them. Apparently, they're outrageously expensive today, almost like real Radio Shack prices. Apparently, you can only buy them 32. My point is, don't buy one of these. Click on the datasheet link. And that'll take you here, okay? So General Instrument, this is like the first commercial UART you could just go out and buy on a single chip. Was actually like the AY whatever the heck. It was a weird chip that required, as you can see, like negative 12 volts and stuff like that. But later on, I guess the fourth version of this was the AY31015D. This is the UART that a lot of people used in their homebrew systems, and what I used as well. And this is the manual for it. If you bought them at Radio Shack, it was stapled onto the little card when you bought the chip on the back. Believe me, I looked all over the place before I recorded this video to dazzle you with my still have it somewhere copy I couldn't find. It's probably wadded up or folded up and stuffed in a book somewhere. But I do vividly remember this diagram and everything else. This is the original manual. The reason I bring all this up is because if you read this, right in here, there's a nice flow chart and a discussion of what happens when this thing runs and how it figures out when data is arriving and when it's not arriving. And it goes on, what is this? Is this the receiver? Yeah, here's the receiver operation. This must be the transmitter, yeah. We're concerned about the receiver when we're talking about this 16-to-1 divisor thingy-mabobber, and it talks about it right here. It's sampled, and it waits 8 clocks, then it waits another 8, and so on. And there's a diagram down here. I remember poring over this. The transmitter timing diagrams. This one right here. Is this the one? No. Let's look at this one right here. This is the ball game. When data arrives on a serial port, it arrives 1 bit at a time. That's why it's serial. Asynchronous data arrives. There's a start bit that's always 0. Then there's a bunch of bits that represent the character. Then you have an optional parity bit. And then there's a stop bit, which is always 1. The way this thing works is it needs to figure out when the start bit arrives, which is a transition from a 1 to a 0. And it needs to do that by oversampling the data so it can kind of calculate and figure out where the middle of the time period is for each one of the bits. And there's a whole simple little protocol to doing that, which is diagrammed down here in figure 11. It says, look, this S1 here, all right, these lines here are the same as S1 over here, okay? So this is a zoom in on right here, is what we're showing right there. So as the clock ticks, going 16 times faster than the data, it shows you that when it sees the serial input go from a 1 to a 0 during one of these clock tick periods, if it's early or late or in the middle or whatever it's going to do, this is what the chip does. It counts out 8 of them. After 8 of them arrives, it assumes that that is the point in time that represents the middle of this bit right here. This is why we have to have 16 or some oversampled speed faster than the data arrives on the serial port. So, in conclusion, do not try to run it at 1x speed, all right? And this will make more sense if you just sit down and think about it on your own. I'm never going to be able to explain it into your head if you don't get it already. Just think it out, and you'll come to realize that this is not a bad thing. It's just there because it's free. It's part of what the silicon does. Just don't use it. Okay, so we scroll down here a little bit, and we get to the nice little diagrams we saw a minute ago. It tells you what each of the registers are for. There's 8 of these things. And it describes that right register 0 has, initialization and reset bits in it. And right register number 1 is how you configure the transmit, the data transfer modes, how you configure interrupts, which we're not using yet, how you configure the receiver, and some other stuff like that, and some specialized synchronous things as well. Okay, so let's go down here. and get to the registers. These are how you read the status, which you don't yet care about. We want to configure it. The code was writing out 1 byte at a time. And what we're doing is writing all of these registers, or at least some of them, okay? So let's see what the code does, and then map it back to what these bits are documented is doing. So, what do we know? We know we write all these bytes out in order, this one, this one, this one, this one, this one, all right? That's what the code up here does, either to port A, if I call this routine, or it writes it into port B, if I call it there. So let's take a look at the first thing that it does. Now, my documentation over here tells me my intention. Okay? Never trust the doc that some user put in there, especially a programmer that's in a hurry. I double-checked this. I believe it's correct. But you probably really want to look these bits up and make sure that what I say here is A, true, and B, matches your understanding of the situation and jives with the doc. Okay? So let's do that. What does this thing do here? DB means define byte to the assembler, and the value of the byte that I'm defining is this number right here. The fact that it ends in B means this is expressed in binary. So I got 000, 11, 000 is the first byte that gets written out into port A control register. Okay, so what does that do? I say it resets everything. Here's write register 0. Which is the register we're writing into. When you reset the chip, it resets all sorts of things. One of the things it does is it configures the control register such that if I write a value into that register, I'm writing into write register number 0. After that, I'm under control of whatever register I want to deal with, okay? So the first thing you're going to do is you're writing into write register 0. Okay, 000, 11, 000. What do we got out of there? 000, 11, 000. So that means these are zeros, which means null. In other words, I'm not telling it to reset these things. All of these are, well, these two things are for synchronous mode anyway. I don't care about this other bit either. I'm just saying don't do anything. And then I'm going to say, what, I got 000, 11. So the 11, that's the 011 right here, which says channel reset. Okay? That's me resetting the entire SIO. No matter what it's in, whatever mode it's in, just reset it. And then all these other bits over here are zeros, okay? And the way this thing works, the way you use write register number 0 is you optionally can do one of these commands and one of these commands. If you don't want to do anything special, you can send these null codes that don't do anything, okay? Then, in these 3 bits over here, what you're doing is you're giving it the address number of the next register that you want to write to. So what I did is I said, don't do anything except reset the entire channel. And the next time I write into the control port on the SIO for port A, I want to write into register number 0. Now, if you sift through the manuals, it will include a comment that says, if you do a channel reset, you must not set any register in here other than 0. Okay? So if I'm going to do a channel reset, you want to do a null channel reset and set this to 0, which is exactly what I did in here. I think the manual goes on to say, actually, that no matter what value I put in here for the next register number, it will be thrown away and ignored anyway. So this is pretty much what you want to do to just reboot the entire SIO, okay? The next thing I'm going to do then is another write to the control port, and because of what I just said, then the second byte here has to also go into write register 0. In other words, I can't combine these two operations if you think that you want to get rid of one of these bytes, okay? So what do I do here? We just looked it up. There's a null command, another null command, don't do anything, and then this value here says the next byte that is that is received by the SIO on the control port, feed it into register number 4. And this is the value that I'm going to store in write register number 4. 01 0001 00. So let's go to write register 4. 01. I've chosen 16x clock mode. Enough said about X1 mode. Don't use it. Okay. What I say? 01. That's this line of code here. 01 000 00. So I got 00 O, and then a 1, and then zeros for these guys up here. So what does that mean? I selected X16. I chose nothing for this. Basically, I chose 8-bit sync character. These are synchronous thingies. I'm not going to run in synchronous mode, so technically it really doesn't matter what I put in there. You read the whole manual, you'll find that out. And then what do I got in here? I chose 01. And therefore, I want 1 stop bit. Okay, when you older folks, when you configure your modem, you choose things like 8 none 1. Well, that sort of thing means I want 8 bits in the character, I want no parity, and I want 1 stop bit. So hiding in here, you'll see the parity and all this other stuff. So my parity enabled was set to 0 because it ended with 2 zeros, right? So what I got here is the none, because I didn't enable the parity, and I got the 1. So this is something none 1, all right? And we'll see the number of bits in the character are set in a different register. And no, don't confuse this thing with how many bits are in the character. This is all synchronous stuff, okay? Ignore these things when you're running in async mode. So after I write this register number 4, and I chose to divide the clock by 16, and I wanted to go with none and 1. And I put a note in here that says if you're using a 1.843.2 megahertz clock and you divide it by 16, the SIO will run at 115.200. Okay? So this means we're not going to use the CTC at all. We're going to put the jumper on jack on J11 for port A. We're going to configure that to run directly off the bitrate clock. Okay? So what do? We just wrote to register 4. Every time you finish writing to a register in the SIO, the SIO will reset itself so that what follows, I said, I want to write into register 4 here. I then put this into register 4. When that is done, it automatically resets itself so that the next byte that arrives will be written into, again, write register number 0. So you do this kind of leapfrogging. I say, I want to write to register 4, followed by here's the byte for register 4. And then I say, I want to write into register 3. Here's the byte for register 3. Then I say, I want to write into register 5. And here's the byte for register 5. So the manual says do number 4 first. So I did number 4 first. I reset it. I write the number 4. Now I'm going to write this stuff into register 3, and then I'm going to come down here 5. So what are we doing into register 3? I got 111, followed by 4 zeros and a 1. And I claim that I'm going to turn on the receiver in the UART, and I'm choosing 8 bits per character. So here's my 8. None 1 is the mode that this thing is going to run in, okay? So what I got, 11101, and that's into register number 3. So I got what? 111, so that's 1 here. That means I want 8 bits per character. I don't want 6, 5, or 7, or whatever, okay? I want a whole byte for each character. Now, auto enables is set to a 1, which seems odd to me, because if you go back to the async operation of the SIO doc in the long-winded version of the manual here, and scroll down right after it says, make sure that you configure WR4 before anything else. There's a paragraph that talks about the auto enables feature. So let's look at this. What this means is it doesn't matter whether I set auto enables to a 1 or a 0, because in the retro design, this is defeated anyway. But let's make sure we all understand the situation. When the auto enables is on, what I'm doing is I'm turning on hardware handshaking. I don't support that in the retro board, although I'd love to. The problem is I ran out of board real estate, and I don't have enough RS-232 line drivers to make it all work. So what this does is it says it stops the transmitter in the SIO and makes it wait until the CTS pin is 0. And that's when I have auto enables turned on. If I turn it off and I put a 0 into auto enables bit, then it doesn't bother to wait. It just simply transmits whenever I give it a byte to send, which is what we really want. Now, if we look at the schematic a little bit here for the SIO in the retro board, you'll see the clear to send is hardwired to ground anyway. So in the end, it doesn't matter whether you set all auto enables to a 1 or a 0 in the code because it's not used. So after this, I'll push up a change and set it to 0 just to try to eliminate any confusion that it might cause. Bottom line, it doesn't matter whether you have auto enables turned on or not in this hardware design. And then there's all zeros for these things. Hunt, phase, this is a synchronous thing. This is synchronous thing. This is a synchronous thing. This is a synchronous thing. All that stuff is off because we want to be asynchronous. And this bit is on up here to let us know, to let it know that we want it to turn on the receiver in the UART. So yes, this comment appears to be correct. Okay, then we move on to register 5. There's a 5 there in binary, and all the other, these are all nulls. I talked about that before. And then we've got what? Right, register 5. This has to do with configuring then the transmitter. So what do we need the transmitter to do? We want, we turn DTR to 0, and we'll see that if you go back to the schematic for the retro board, that's actually connected up to the printer port. And I wanted to make sure that I explicitly set it to 0 here. It doesn't really matter for the SIO, but in the grander scheme of things, you probably want to set this thing to 0. And then we turn on the transmitter so we can actually use it. And we also want the transmitter to use 8 bits per character because we can have the transmitter and receiver running in different modes if we really want to. Don't do it. It'll just confuse the crap out of you. So what do we got here? 0101 with a bunch of zeros. 0110 1000. So that's register 5. 011. There's my 8 bits per character. 01 is the transmit enable. Okay, I'm not sending a break. Again, research how RS-232 works. Break is an alert type of signal that you can send down the line. We don't want to do that. SDLC is synchronous. RTS is also one of the pins that I hooked up to tinker with the printer. And it's set to 0. I probably should add that to the dock. And then the CRC stuff is also deals with the synchronous stuff. So the only thing I really want to do is turn on the transmitter and leave everything else alone in this group of bits. And that's exactly what this does. So when the code says SIO-A in it and then SIO-B in it, it sets both ports the exact same set of configurations. We're running an asynchronous mode. Divide the clock by 16. If I jump J11 to the clock oscillator directly, both ports will be running at 115.2. 8 bits, no parity, 1 stop bit. Okay? All right, so let's go back then to the hello program. So we will have done the initialization. This is not in the code. We then would go right into hello A, print out this string here, 1 character at a time, and then halt. So this should work fine if we compile these programs, or assemble them, I should say. Okay. We just ran SIO1.asm. We just assembled it. So we want to program this. And in the README, as you can see on the GitHub page, I put in here and it says, if you install the programmer that I gave you in another project, and you install the code and you compile it. We went over this in the part 1 of the system test code. This is how you can run the programmer and write your binary file into the flash on the retro board. Okay, so that's what I've got. It's plugged in. It's all ready to go. And I forgot the name of the file. We want to get hello1 right there, .binary. Now I'm going to bring this serial port. This is like when I'm running Minicom or something like that on my Linux desktop. And this is connected up to the serial port on my PC, and unfortunately by resizing the window I lost the status bar down here. Let's go ahead and reprogram the flash and I'll show you what's going to happen here in a minute. See where it says hello right there? That's a good sign. Why does that? There we go. If you hit Control A, what is it going to do? Z, it's in the configuration mode and all that. Oh, you know what it's doing? The terminal window is too small. That's funny. If it doesn't have at least 25, what a garbage app. If it doesn't have 25 lines, you can't see the status bar, I guess. And this is what I wanted you to see. So what did we do? We configured it for 115.2, 8 none 1. Okay? And it's emulating a VT102, and this is I plugged in a USB cable into my Linux box, and then I ran Minicom on that. Okay, so you saw the hello pipe out after we reflashed it, and because the Raspberry Pi asserts and deasserts the reset signal, we talked all about that. After it does the flash programming, it also then resetted it. It came out of reset and did the code and printed out our hello. So this is the proof of life, the serial port version of Blinky, your hello world. And it does exactly what we want it to at the right bit rate and everything else. Now let's look at some of the other variations of the code in here. What else is going on here? So I have hello A, and then commented out I have these spew, echo, and stuff like that, all right? Let's look what spew loop does, all right? Instead of falling down here and halting, let's uncomment this thing. So after it says hello, it'll run this thing here, all right? Let's see what that is. That's the code sitting down here. Spew loop. What's it going to do? It's going to put a space into the B register. It's going to call transmit a character. We didn't actually look at this code when we were poking around the SIO driver. I'll look at that in a second. So it's going to print the character in the B register just like hello did above. And then it's going to add 1 to the B register. And what is it going to do? It's going to load 7F into the accumulator, compare that to the B register, and if B is not, jump if none, 0, this means if these are not equal to each other, go back up to spew loop 1 and do this over and over again. So what's going to happen here is the B register will start at hex 20, and it'll go up one at a time until it gets to 7F. When they become equal, this compare instruction here, compare B means compare the accumulator to B, and when they are equal, the 0 flag will be set in the ALU. If you look up these instructions, that's what it does. This is how we figure out, does A equal B? Well, if the Z flag is set, they're equal, we then fall down here. When that happens, we print a carriage return in a new line, and then we go back up to the top of spew loop, and we reset B back to 20. So we're going to just do this in a loop. So what's that going to do? Well, if you look at the man page for ASCII, what you'll find out is hexadecimal code, where are we? In hex, this column right here. Hexadecimal code for 20 is the space. 21 in hex is an exclamation point, blah, 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 blah. The 30s are the digits, and then we get some special characters. 3F is a question mark. Then when you get up to number 40 over here, that's the at, and the A is in hex 41, and then you go on to Z, a couple more special characters, lowercase, a few more special characters, and 7F is the last defined character in here. So what is it going to do? It's going to print out a bunch of special characters, numbers, uppercase, lowercase, less, curly braces and a tilde and some other stuff. And it's going to just do that over and over again on each line that it outputs. We reassemble it because we brought in some code that was commented out. Let's bring our terminal back in here, and we're going to rerun our flash command on the same file because we just modified it, and we'll see what happens now. It's going to print hello, followed by go into a loop, and then it's going to print out exactly what we'd expect. Start with a space, add 1, go through all the ASCII characters one at a time until you get to the 7F value, and just spin like crazy. So this is running at 115.2, which anybody who's ever used CP/M in their entire life would tell you this is insanely fast. because most terminals, in fact, I don't think any of them did back in those days. 9600 was crazy fast in 1980, right? Maybe 192 was about as fast as anything ever would go. So this is 6 times faster than ludicrous speed, as you might say, back in the day. So that's a good sign. Let's rerun our editor and see what the other things in here do. What we wanted to do, by the way, is look back at the SIO.asm driver, at what it means to say write a character. So we just called SIOA txchar to print out each of the characters that is spewing on the console one at a time. And we add one to the B register and go around the loop over and over again. So the comments here says it prints the character that's in the B register. While this code runs, it will clobber the accumulator, the flags, and the C register. So how does this thing work? Well, there's an SIOA transmit and an SIOB transmit. The same kind of logic that we saw with the init logic above. What we're going to do is we're going to put the port into the C register that we want to, interact with. So if I call SIOB, it's going to put the control IO port address into the C register and go down here to this guy. Otherwise, I'm going to write to the A port. I'm going to put the A control register IO port address into the C register and fall through to here. What am I going to do? I'm going to read from the control status byte. Okay, the control port. So remember, during the initialization sequence, all we ever did was write to the control port. Now we're going to read from the control port some value. So let's see what that means in our documentation over here. There's 3 readable registers. Read register 0, register 1, and register 2. We don't care about registers 1 and 2. Right now. This deals with, obviously, interrupts. This is some more advanced status information that we don't care about right now. And read register number 0, which is the thing you get if you just simply read from the control port, gives you a bunch of bits that tell you about what's going on. Like, is there a character available? Did it receive a character since you last looked in there? This will be set to 1 if that's the case. And it's not receiving anything. I'm not sending it anything, so that's not going to happen. Is there an interrupt pending? Is the transmitter buffer empty? This is key. All right? That's what we're really looking at. These other ones, these are for like synchronization routines and stuff like that. And here's, did someone send you a break signal? Remember I mentioned that earlier. It's some like alerting signal that you can send down the line. Don't care about that right now. We do care about when we can send something out of the retro board, and that's what TX buffer empty means, which is right here. We got 1, 2, 4, 8, 16, and so on. So if I AND this with a 4 in hex, I probably should have ANDed it with a binary number, so you can see 0000100 in here, but we all know how to count, right? I certainly hope so. You're going to have to get used to that big time if you're going to write assembly language code for just about any processor. You have to think in binary, hex, and decimal, and sometimes octal, and jump between all those number bases quite fluently and on demand, okay? So what we're doing is we're watching this buffer empty bit right here. And when that bit becomes set to a 1... and we did an AND operation with ALU, the value of the accumulator ANDed with this value here. If the bit in that position is a 1, it will represent a non-zero value. If it turns out that that bit is a 0, and then, in other words, the transmitter is currently not ready, it's busy, it's sending the character that you just asked me to send before, okay? Then it would be 0. And if it is 0, we want to go back up and spin around here waiting forever. Okay? So we wait until it is non-zero, and we fall down here. And what we're doing here, the idea was I wanted to be able to reuse this code for both ports. Maybe it's a bit gratuitous, but that was the goal. It turns out if you put the control address in the C register, the corresponding data address for the same port, same channel, is 2 address numbers less than the control port. Okay, so by saying decrement C twice, I reposition C to point at the data register, where if I output the value from the B register, which is the thing I want to print, okay, I'm sending it into the transmitter of the SIO. It's as simple as that. That's all we got to do. Then we return back to where we came from, which we already looked at. It's the thing in the counting loop in the main program, and that's all we got to do. And receiving data is exactly the same logic, except for I'm gonna read data instead of write data. And when I do the AND operation, I'm reading from the status, the control register. I'm going to AND it with a 1 instead of a 4. And I'm going to do the same thing with a little loop in here, because bit number 1 is the receive ready indicator bit. Okay? So we can receive, we can transmit. This is all we really need to be able to do. Up here on the top, there's some other routines in here that we don't use in this particular example. What these do is it allows me to just simply ask, is the transmitter ready right now? And it'll return a non-zero status if it is in fact ready. This is the same logic we just looked at below in the loop, but this allows me, by defining a standalone version of this, in my regular old programs, I can just ask it if the transmitter is ready without actually having to send anything. So I can poll it and play some games if I want to in my program, and we'll see that in a minute. So there's a transmit ready for A, transmit ready for B, a receiver ready A, receiver ready B. And in theory, I could just as easily call these from the code down here. But if I did that, I couldn't use this, use the register C the way I'm doing in here, all right? So it's a mildly replicated code, but it's okay, all right? Why? Because I said so, and I'm not going to fix it. Okay, so let's go back to our main program here. So we're in this spew loop code that is still running right here, okay? Let me get this out of the way. Let's go ahead and put that back off again and turn on the echo loop program. So let's see what that's going to do. It's in the same file here. Oops, scrolling problems. What does it do? I'm going to receive a character from port A. I'm going to then put it in register B, and then I'm going to transmit it. All right, I forgot to read the doc. Well, we were poking around in there. The receive logic returns the character that has been received in the accumulator, in the A register. That's why I have to copy it into the B register in order to transmit it. Okay, and the transmit logic requires it to be in B. Okay, so what do? I read a character. It's going to wait forever, by the way, and when it receives one, it'll return it in the accumulator. I put it in B, I transmit it out. And if it's not ready to transmit right now, it'll wait and transmit when it's ready. And then it'll return, and I'll go back up to the loop here. So all it's going to do is echo back whatever characters I send it. And if I remove this comment here, it'll add 1 to the character in here, right? So if I send it an A, it'll come back with a B. If I send it a J, it'll come back with a K, and stuff like that, right? Well, this is commented out right now. I'll leave that as a test to the viewer to play with that if they want to. Actually, I won't. We'll turn that back on in a minute, and there's a reason why I want to do that, and we'll see what that is in a minute. So, all right, I'm going to reprogram it again. Let's go ahead and bring the terminal down so we can see the magical reset. Okay, so it printed out hello because it's still commented in, and it's not going to spew anymore because I commented that out. And if I type ABC, you can see the ABC come back again. All right, 1, 2, 3, 4, 5, and so on. So that's obviously working. What do we just test there? We test the ability to receive as well as the ability to transmit. Okay, that's nice. And it's not going nuts. The status must be working. Otherwise, it would probably be spewing garbage. If it accidentally thought there was data when there really wasn't, it would be printing, the same thing over and over again, or garbage or whatever. Okay, so that's a good sign. So that also means that the send and receive pins on the DB9 on these console ports down here are set correctly. Now, you'll either have 2 shunts in the right half when you view the board this way, or you'll have 2 shunts over here like this on the left half of the 5 pins. So I laid it out like this on purpose, so you could just take these two shunts. It turns out that I don't even have two cables that match on my own lousy workbench. So I built these two ribbons. I had a video earlier on how to make the IDC connectors and press them in with a vise and all that, and a DB9 on the other end. And these cables are identical, but the null modem adapters that I needed to plug them into my my PC, my gender reversers and stuff like that, because I used male pins on these particular cables, and the PC serial port also has male pins. I had to put gender reversers on there, and I had two different brands. That's my point. So one of them's DCE, one of them's DTE. If it doesn't work one way, just pull these two jumpers out and move them to the left and put them back in, okay? This will effectively reverse pins 2 and 3 on this cable. Same over here. The other jumper of interest is J11 up here. When these jumpers are on the right, again, is a board in this configuration, what we're doing is we're connecting the 1.84 megahertz crystal right here directly up to the SIO bitrate clock inputs. When you move these over to the left, what we're doing is we're hooking up the CTC chip, which is this thing right above here, instead to drive the SIO. And in this video, we're not initializing the CTC, so it's not a good idea to put these on the left. You want them on the right, just the way they're shown right here. Okay, so this is how I jumpered my board. Some variation of these down here should work for you. All right, let's look at now the bit about this comment and why did I change my mind is because I forgot. The main reason you do stuff like this is it's too easy to fool yourself into thinking that this thing might be working. Some terminal emulators will echo back on the screen any character when you type them. So I could be lying to myself, to you, whoever. I don't know that this is really working right. Because I could have this thing I could have the terminal configured to echo, auto echo stuff back that's typed. And it could be that the retro board's not even plugged in. And it would still look like this. All right? But if I go in here and I receive a character and I add 1 to it and then I transmit that, there's no way I can accidentally have that fake me into believing that my code is actually running correctly. Never write dumb test programs. Write smart test programs, okay? So that's what this thing is going to do. It's a little less obvious, but now if I hit A, I'm getting B's. If I hit B's, I'm getting C's. If I hit 1s, I better get 2s, and so on. No argument there. That's definitely doing the right thing. It's definitely receiving a character, it added 1 to the character code, and it sent that back. You can't accidentally get this to do this. It's unlikely. Okay? That's a pretty good test. Okay, so now what are we going to do? What else do we have in here? Lots of goodies. Let's turn the echo off and turn the relay on and see what that thing does. So where's the relay routine? All right, so here is the relay code. What does it do? It calls those ready routines that we just looked at. It says, is the receiver ready on port A? If it's not ready, the 0 flag will be set, and it comes down here to relay B. And it asks, is port B ready? Well, if it's not ready, the 0 flag is set, and then it then goes back up to here to the main relay logic up here. So it's going to go back and forth and back and forth and back and forth. As soon as there's a character ready on port A, it'll fall down to here, and it'll read it. Receive the character on port A, put it into register B. We saw this in the echo routine. But look closely. I'm going to read from A, and when I get it, I'm going to write it out on port B. Then I'm going to fall down here, and I'm going to check if B is ready. If it is, it'll fall down, and it'll say read from port B, copy it into the B register, and write it out on A. So what this is going to do is it'll copy any data that arrives on port A over to port B, and it'll copy any data that arrives on port B, which is this guy right there, and it'll copy it back onto port A, and it'll go around this loop, skipping over the reading if the thing is not ready yet, okay? So here's my terminal on port A. And here's another terminal on port B. So let's run this routine. Let's comment, make sure I commented it in. I can't remember. I can't remember back 3 seconds ago. Okay, here's relay right there. Okay, compile it. And then go rerun the Flash program. Let's bring the terminals up in here. We can see how it's going on. When it boots up, it printed hello on terminal A, as it always does. Terminal B is not entirely in view. Let's bring that down. It didn't do anything, and I have some noise on the screen from running other tests earlier. So if I type in here, this is port A. You see I'm hitting a couple of capital A's now. You see it showing up here in port B. If I type in port B now, a bunch of ones, you see them showing up down here in port A. Okay? So that's pretty cool. I now know that both ports work. They're both wired in correctly. They both, the RS-232 line driver's connected right. The jumpers are all in the right place. I can cycle data back and forth between these two terminals quite easily. Now, I can also cut and paste in here because I'm a Linux machine, and I can just spew like crazy if I want between these two terminals and get whatever I want to do and send it back and forth that way if I really want to. Okay? So that looks good. And I can copy things back and forth between the two terminals. Fantastic. Okay, what else do we got that we can play with in this program? Well, we've got this hex dump stuff that I have all commented out. All right, so let's go ahead and set this to 1 and look and see what this is going to do. Now, I have a very simple, very primitive library that I wrote that generates hexadecimal dumps of data in memory. So we can just print out the contents of memory if we want and see it on our screen. And that's what's in this library down here, this hexdump.asm file. Okay? Now, if we look through this file and we look for hex dump, we can find various labels. There's the, if it is defined, what are we going to do? We're going to zero out, or rather I'm going to set what? I put A5 into memory from address FFOO, and I'm going to then copy that to FFO1, and I'm going to do this 255 times. We talked about LDIR before when we copied the data out of the flash up here. What this one's actually going to do is it's going to say, copy the data from FF00 to FF01, and it's going to leapfrog 1 byte at a time. And before I start the LDIR, I'm going to set the first byte to A5. So what this is going to have the effect of doing is it's going to put A5 into this address, because that's what it means to put the parentheses around HL like that, put into memory the address of the HL register, which is this value right here. Then put this number into the DE register and this count into the BC register pair, and say LDIR, which is load, increment, repeat, which means read from the memory at the address in HL, which we just put at A5 in there, write into memory at the address that's in DE, which means it's going to copy the A5 from FFOO to FFO1. Then it's going to count it by decrementing the BC register and ask if BC is not yet 0, go back and do it again. After these things have been incremented, we'll then be reading from FFO1 and writing into FFO2 and so on, all right? So this is how you can just pad memory with some value. And what this is going to do is it's going to fill in the memory from FFOO to FFFF with the value of A5. That's where our stack is, okay? So when I call SIO init and SIO init, and I'm using the stack, to save registers and deal with our return address and all that other fun stuff, it will be modifying the values in memory in this range up here. So when we're done initializing things, I can come down here and I can then dump out by calling the hex dump routine, and that's the whole point of this, ranges of memory. First thing I'm going to do is I'm going to dump out the values of the memory that are the code itself, from 0 in the Z80 address space up to _end, which is the same sort of thing we did when we copied out the flash. There's the end down there. I talked about that last time, okay? So it's just going to dump out the RAM contents For crying out loud, I gotta find the logic here. This is going to dump out the RAM contents from 0 up to _n, which is the executable instructions and stuff like that. And that's what this is going to do. The HL is the address to start dumping. BC is the number of bytes to print. The E register is a 1 or a 0, depending on whether I want to print it out in a fancy mode or a non-fancy mode. We'll see that in a minute when we look at this code here. When I'm done with that, I want to dump out the stack region from FFOO for 256 bytes in a fancy formatted routine so we can see what happened when we initialized the SIO ports. Because we padded it with A5, we then used it. So when we dump it out down here, we'll be able to see how much of the stack was written into and what values were written into there when we were doing these initialization routines, okay? And that's all we're going to use the hex dump stuff for. It doesn't get used down here, all right? So let's look at the library for the hex dump routine, which is in this file right here. And see what this one does. Oh, surprise! Dump BC number of bytes from memory starting at the address in HL. If E is 0, then do not fancy print the output. If it's 1, do print it with fancy stuff. This does not clobber any registers, and it does that by just simply saving them all in the stack before it does what it is going to do. When it's all done and it returns back to the caller, down here somewhere you'll see it popping all the values back out of the stack and going back to the caller. Okay? Now, I probably should have documented this thing, but for the most part, I'm going to leave this as a task for the viewer. The bottom line is there's a loop in here, and it's going to count using the number in the BC register. This is going to go round and round and round and round, and what it's going to do is it's going to print out the values from the memory in hex form. And it's going to do this by calling this hex dump 1 routine, okay? So it's going to go around and round and round, and 1 byte at a time, it's going to print out the bytes. Now, while it's printing, it wants to put a carriage return after every 16 bytes, and it wants to put the address number on the left in the usual form for hex dumps. So we want to print out the value of the HL register when we're at the beginning of the line, and we're going to put a little colon after it. That's what's going on here. Then we're going to put a space. Then we're going to follow around. We're going to go up around this loop, and we're going to then what are we going to do? We're going to grab the byte that's in the memory and put it in the accumulator, and this is the thing that actually will print out the 2-digit hex value that is in the accumulator. Then we're going to add 1 to the HL because we want to ultimately print out the next byte and so on. And what are we doing? We're restoring the current BC register. Remember, this is the count, how many bytes to print. So you would expect to see that be decremented in here somewhere. And then we're going to save it back in the stack. And then what are we going to do? We're going to check to see if we have depleted it. We want to know if the BC register pair became 0. And the easy way to do that is to put B into A, then OR A with C. I mean, think about it. What happens when you do that? All the bits of B then are ORed with all the bits of C. If any bits anywhere are a 1, then we know the BC register pair is not equal to 0. If, after you do these 2 instructions, the accumulator has a 0 in it, then we know that B and C combined had the 16-bit value, and that pair was all zeros, okay? So if it's not equal to 0, we go back up to the loop, and we just print another byte and print another byte and so on. When we're done printing all the bytes, this ultimately becomes 0 and falls down here, prints carriage return in a line feed. We'll see that little subroutine down below. Clean up the registers and return to the caller, okay? So here's the hex dump routine that prints out 1 byte in the accumulator. Now, this is not the optimum way to do it, but I would argue this is the easy-to-understand way to do it. What do? We save the accumulator. We shift A to the right 4 times. Now, why do we need to do that? We want to print the 4-bit hex digit that's in the left half of the accumulator, the most significant digit first, because we read from left to right, and if A has a 1 and a 2 in it, the 1 in hex would be in the left side of the register. So we want to shift it over to the right. And then we're going to call hex dump nib, which prints a 4-bit nibble in the least significant half of the accumulator. When we're done with that, we're going to pop the original value back again. We're going to AND it with 0f, which is going to just simply leave the least significant 4 bits in the accumulator with the most significant all zeroed out, and then fall into, in other words, call it again, the nibble routine. And when we're done with all that fun stuff, we're going to print out the character. And this is what we call a tail call. By simply jumping to the transmit character routine from here instead of calling it, what happens is when this routine returns, it'll return to whoever called hex dump A. I could just as easily have said call the transmit character routine, but the very next instruction here would be a return instruction. So I return to a return back to... You can just jump over here, okay? When there's nothing else left to do, this is how you make that work, okay? So what happens... okay, bird's eye view here. One nibble at a time. So we want to print the least significant 4 bits in the accumulator. That's what's going on here. So if I add a 0, in quotes, what I'm really doing is adding the character, the ASCII character code for the number 0 to the accumulator. So if the accumulator has a 0 in it in binary, by adding this to it, the value in ASCII, remember I want to print this out in ASCII, will be then 30 in hex, because the hex value of an ASCII 0 is hexadecimal 30. The ASCII value for a printable 1 is a 31, and so on. So what does it mean to print out the accumulator in hex, or at least the least significant 4 bits? Well, if the value is between 0 and 9 inclusive, we need to send a 30 through a 39 in hex out to the SIO so we can print any one of these values. If it's greater than 9, we need to move over here and print out A, B, C, D, E, and F in order for it to be a hexadecimal value. So we have to adjust it. If it's greater than 9, we need to move up to start 41, 42, 43, and so on. So this here is enough to make the accumulator hold the values 30 through 39 if the value is less than 10 in decimal, right? Or less than A in hex, okay? Then we can ask, look, is the value in the accumulator after I did this more than the printable character for a 9? In other words, is it, should it be an A through F? Okay? Well, if it is less than that, then just print the value as it is. That's what happens down here. Okay? If it's greater than or equal to the 9, it means I need to print an A, B, C, D, E, F. How do I do that? Well, if I take the A and I subtract the 9 and I subtract 1, what happens is this expression here will represent the value that is the difference, the number of extra, how far away am I from the A, right? So let's say I have an A stored in the accumulator and I add this printable ASCII 0. It moves it up to this, 30 plus the A that was in the accumulator. So it would actually then be equal to 3A. And I don't want to print a colon. I want to print the letter A. I want to get a 41 in there. Well, if I take 41 and I subtract 39 and then I subtract 1 from it, that would be the number that I need to add to a 3A in order to move myself up to a 41 to get the actual A into the accumulator, which is what I want to print, okay? Work it out on paper if it's not obvious, okay? This is the more obvious of the various ways to do this. Arguably, okay? So either way, this will print the most significant digit that's in the accumulator. And when it goes down here and it jumps to the print routine and it does a return, this will then return back to the call up here. It'll pop AF, it'll do this, and it'll fall down and do the other digit, the least significant half, go down here, jump to the print routine, and then when it returns, it'll return to whoever called hex dump A, which is this logic up here, okay? You see it calling hex dump A, and so on. So that's what's going on in this loop. This logic down here just simply prints a carriage return and a line feed, so that when we get to the end of the line in the dump, we go back to the beginning, and that's a little subroutine that takes care of that. He's played the same game with a tail call down here to save a byte of memory, which is what you do when you only have 64K to work with, okay? So let's compile it again. Let's rerun this into the firmware. Where's my history? There it is. So this is port A. So this is not going to do the relay anymore. This is going to just go and dump a bunch of stuff out in hex. So the hex dump here, remember, is the firmware programmer on the Pi. The hex dumps here are what we just printed out in the program that we wrote. So when it started and it rebooted, it went to the beginning of a line. It was garbage on the screen. Let me reach over and press the reset button and restart this on a clean window. Okay, so we can scroll to the top and see what the heck's going on. So what did it do here? It printed out, what it actually does is it prints the hex dump out of the data that's in the memory that is the executable program up into the end. So that's what we see up here, okay? Address 0 through whatever this is, 171, okay? Then we dump out FF00 to FFFF, and this is the area where the stack would be. So you can see that we padded it with A5s with the LDIR, and you can see some junk up here. This is the values that are stored in the stack by the hex dump routine, saving the registers and calling subroutines and stuff like that. And then we would expect to see stuff like that in there. When it's done dumping all this stuff, it goes into the hello routine, and I don't know, is it running the echo or something? I don't remember which program it falls into, or it might halt. I don't remember. Let's see. Where did we leave the code? Back to the top here. Well, that's the hex dump routine. We don't want to see that. We want to look at the hello. Serial 1. For crying out loud. There we go. Yeah, so there's us padding it. We initialize it. We hex dump out the code. We hex dump out the stack region. We go to hello A, and it fell through to our usual relay routine down here. If we change it back, we can obviously put it back into the echo code, which is probably still set to the increment, where if I send it a 1, it comes back with a 2 and stuff like that. So let's go ahead and run it again, now that we know what we've actually done here. All right, so if I type a bunch of stuff, we can see what's going on here. Now, if you hit, what do I want to do? Hit various control signals. It's really disorienting when I hit the 1 key and I get a 2. If I want to go down a line, that would be Control J. But that will come back with Control K, which means to go up a line. So I need to hit I to go down a line. Control I would be +1 equals Control J, which means to go down a line. All right. Control L normally would clear the screen, but if I do this, it'll send back a Control M, which will go to the beginning of a line. So if I hit Control K, it'll clear the screen. So this is very disorienting. You might need to spend some time with the manual page for the ASCII character set in order to think out what I just explained, okay? So these various thingies here are the control keys I was just talking about. And if you look at a row like this, Control J, remember I said it was supposed to go down a line? That's the OA, and that's the \n in a C, C++, or any modern programming language. That's the new line, right? The return, go back to the beginning of a line, is Control M, and Control L is called form feed, which on a terminal will just clear the screen and so on, okay? Horizontal tab, backspace, and all that. All these different codes for this stuff. My point is, I know what most of these codes are, but when you're running a program that, where's my editor here? that adds 1 to whatever key you spend, before it echoes it back, which is what happens here, it's very disorienting. So maybe if you're going to just play around and you do want to echo, you might want to comment that back out, okay? I'm just saying. So here we go. Here we are back in normal mode. If I say A, B, C, D, E, F, G, we get that. If I hit the return key, it'll go to the beginning of a line. If I hit Control J, it'll go down a line. If I hit Control K, it goes up. And I hit Control L, and it'll clear. And everybody's having fun now, right? Of course. Hello. So, there's the basics on get the SIO to work in pulled IO mode, a little bit of hex dumping in there and some other stuff. So I hope this has been useful. Let me know in the comments below, especially if you got any great Radio Shack out of stock stories. I'd love to hear about them because, you know, I mean, again, anybody of a certain age, that was your life back in the day. Sorry, temporarily out of stock. Anyway, thanks for watching. I'll see you next time. Bye-bye.